In this video, we're going to take a look at some longer answer type questions on the waves and optics topics. So let us start off with some refraction, it looks like. So we've got a rectangular glass block A, B, C, D. And we've got a light ray incident on it with an angle of incidence of 60 degrees. Okay, so the ray FE is partly reflected and partly refracted at E. Draw an approximate path for the refracted ray within and beyond the block and then label it refracted ray. So it's going into a higher optical density, so it's going to bend towards the normal, or our angle of refraction is going to be smaller than the angle of incidence. And then once it exits the block, because it's rectangular, the ray is going to be parallel to EF. And that's our refracted ray. And we also need to draw on the path of the reflected ray. So the angle of reflection should be approximately equal to the angle of incidence, i.e. 60 degrees, and that's the one in purple, our reflected ray. Okay, so second ray, almost parallel to AE, strikes the block at E and is partly refracted at an angle of refraction of 43 degrees. State an approximate angle for the value of incidence. So AE is basically going along the boundary, so that's going to be at 90 degrees to the surface, and that's going to mean our critical angle is going to be around about 43 degrees. So we're accustomed to seeing critical angles when it's in the glass and then goes along the boundary, but there's no reason it can't also be created by sending a light ray along the boundary and looking at the angle of refraction as well. So that's how that one works. Calculate approximate value for the refractive index of the glass of the block. So we're going to be using Snells Law here, and I'm going to use this form of it, and I'm going to use this form throughout the video. There are some other forms out there, but I think this is the most useful one. So we want the refractive index of the glass block, so we want N2. You know, N1 is 1 because it's in air to start with, so we are rearranged to make N2 the subject, and we can get rid of N1. We can plug our numbers in. I, remember, was 90, sine of 90 is 1. That gives us N2, which is 1.5 to 2 significant figures. The speed of light along the ray is 3 times 10 to the 8. Calculate the speed of the refracted light. So we're going to essentially use the fact that refractive index is speed of light in a vacuum, or air, they're the same, divided by speed of light in the material. We rearrange that to make the speed of light in the material the subject, plug the numbers in, and we can see we're going at 2 times 10 to the 8 meters per second in the glass. So 2 students are asked to determine the speed of sound in air on the school playing fields. List the apparatus that they need. So when we want to measure the speed of sound, we usually use we can use a reflection method, which is a bit complicated, or we can use the difference between the speed of light and the speed of sound, which is much easier to do. So what we do is we need some sort of noise making equipment, maybe cymbals, maybe a starter pistol, anything like that. We need a tape measure to measure a distance, and we need a stopwatch to measure a time, and that's all you actually need. So what they need to do is measure the time between seeing an event and hearing it. And what we're going to do is assume that the light takes basically 0 time to get to us, so the time difference tells us how long it takes the sound to reach us, because light travels something like 1,000,000 times faster than sound, so that's actually quite a good approximation. And you also need to do is measure the distance of the observer from the event. Those are kind of the 2 measurements we need. And then to get speed, we're just going to do distance divided by time. That would give us the average velocity of the sound, and we're going to assume it's constant, so we're saying that's the speed of sound. State one precaution you'd take to improve the accuracy. So what you'd really need to do is make sure that the time isn't really small, because it's going to be the time that the measurement of time that tells you how accurate it's going to be. So we need to ensure the observer is a long distance away, so there is a clear measurable time between seeing the event and hearing it. If those two are too close together, there's going to be a large amount of error in your measurement. So the table gives some speeds. We want the speed of sound in air and the speed of sound in water. So the speed of sound in air is about 330 odd, so we're going to put a cross in here. speed of sound in water, sound waves, which is a longitudinal wave, travel better the higher the density of the medium. So water is much more dense than air, so we get a step up in the speed, and then if we move into a solid, it gets even faster than that. So I think it gets up to about 5,000 in a solid, so we'd probably go closer to 10,000 there for a solid. Okay. So now we're going to look at drawing some ray diagrams with lenses, it looks like. So we've got an object O, and we've labelled the tip of it, and it's got a convex lens here. And we've got the two principal foci of the lens are marked, and they're equal distances either side of the lens. Draw the path of two rays so that they pass through the lens and continue beyond, and then complete the diagram to locate the image of the object and label it I. So there are two rules which you use for questions like this. Parallel rays of light go through the principal focus, and rays of light that go through the center of the lens continue straight on. So if we draw a ray of light that comes in, we call these like parallel to the lens like this, it's going to get refracted through the principal focus like you can see, and from the same point we're going to draw one that goes straight through the center of the lens, which, as I just said, gets undeflected. So the problem we can see at the moment is that they're currently diverging, so they're not going to form a focused image on that side of the lens. So what we do is we can extrapolate backwards and see that the lines will virtually converge at this point here, and that's where the virtual image will be formed. And we can see a few things about the virtual image. It's the same way up as the object, so it's upright. We can see it's bigger or magnified, and it's on the same side of the lens but further away as the object. Okay, so those would be the things I'd look to describe it, and we describe it as virtual because no light rays actually converge at the point where the image is. It's just an extrapolation backwards. It's a trick of our brain in the way it processes things. Okay. So looking at a different situation, our object is now outside the principal focus. So we're going to repeat the same process, draw in a light ray that goes through the principal focus, draw a light ray that goes through the center, and we can see this time those two rays do converge on the opposite side of the lens, and that's where our focused image would be formed. So we can put that in. We can see that image is going to be upside down. We can see in this case that image is smaller than the object. It's closer to the it's closer to the lens than the actual object is, but that is a real image forming. We do actually have light rays passing through that point and converging to form a focused image. So if we move the object closer to the lens, what's going to happen is the image size is going to get bigger, and what's also going to happen is the image is going to move further away from the lens. So that's how we create bigger images. The image gets moved further away, but it does get bigger. And then if we move it so it's inside the principal focus, it's going to switch from being real currently to a virtual image. The image is going to continue to get bigger, and then it's going to become upright, whereas it's currently inverted, and the image is actually going to move positions from the left to the right hand side of the lens. Okay, so we're going to look at a wavefront model of light. So this is very much how Huygens, or Huygens, however you want to say his name, envisions the passage of light. So first we've got them approaching a plane mirror, and then we've got them approaching a rectangular block. So he wants us to draw wavefronts to show what happens. So the first one is reflection. So I'm going to draw where the ray of light would go. So this is how Newton imagines light, the passage of particles, where we can see the angle of reflection equals the angle of incidence there. And the wavefronts are always perpendicular to those rays. And the key thing to convey here is the wavelength doesn't change during reflection. So those wavefronts should have a fixed distance between them. With refraction, again, I'm going to start by drawing the ray of light, which would bend towards the normal because you're entering a material of higher refractive index. Again, our wavefronts are perpendicular to that ray, but the first thing to remember is they don't change direction until they've crossed the boundary, which is why I haven't extended those lines back out across the boundary. And the other thing is the wavelength is going to decrease. So the speed of the wave decreases as it crosses the boundary. The frequency doesn't change, so therefore the wavelength has to be smaller as well. Okay, so in the diagram, the waves are approaching the block, have a speed of 3 times 10 to the 8, so they're in like vacuum or air, and the angle of incidence is 70, refractive index of the glass block is 1.5. Calculate the speed of light waves in the block. So we're just going to use the same equation we used before for refractive index, rearrange it and calculate our speed, so nothing really different here. And again, we're going to calculate the angle of refraction, we're going to use Snell's Law. It started at 3 times 10 to the 8, so we know n1 is 1. This time we want the angle of refraction, so I do this by making sine r the subject. I calculate what sine r is, the value, and then I'll take the inverse sine of it to get the actual angle, which is 39 degrees to two significant figures. Okay, so in an optics lesson, a physics student traces the path of 3 rays of light near the boundary between medium A and air. The student uses a protractor to measure the various angles. Okay, so this is our first one, and we can see it is bending away from the normal as it goes into a lower refractive index. Makes sense. Then we've got what looks like the critical angle for the second diagram, because you can see it's going very close to the boundary. And then the ray 3, it looks like we've got total internal reflection occurring. All right, so those are our diagrams. State which is the optically denser medium, A or air, and how can you tell? It's going to be A because the light bends away from the normal when it's refracted. We could also say A because total internal reflection only occurs when you go from high to low refractive index. Either of those explanations would work. State which medium the light travels faster. It's going to be air because we were essentially doing the opposite of the last question. So we said optical density is higher in A, which means its speed is lower because they are inversely proportional to one another. High optical density means low speed. Critical angle we can get from the second diagram, so we're just measuring between the ray and the normal, which gives us 42 degrees. And the process in diagram 3, as I said when I was looking at it, is total internal reflection. The angle of incidence is bigger than the critical angle. Refractive index of medium A is 1.49. Calculate the angle of refraction of ray 1, showing all your working. So again, let's get all of our measurements together. We know what the angle of incidence is. We know that the refractive index of the first substance is. We know it's going into air, so we know the refractive index of the second substance. So we can use Snell's Law, and I'm going to go through the same process I did before. I'm going to calculate what sine r is, and then take the inverse sine to get what r is, 59 degrees. And then again, similar process before. If we want to get the speed, I'm going to use the refractive index. We know what the speed of light in a vacuum is, we know what refractive index is, so we can calculate it, and we actually basically done the same calculation we did before. So we're going to do some more diagram drawing, but we're going to do specifically for virtual images. So the first one we're going to do for a mirror, and then we're going to do for a convex lens. So we want to show the position of the images. So for the mirror, I'm actually going to cheat slightly here. So we know with a mirror, the mirror image is the same size and is an equal distance from the mirror as the object. Okay, so I'm going to put that in straight away. And then we need to actually show where we've got that from. So what I'm going to do is I'm going to just draw 2 lines back from the tip of the object to the mirror. Now, the way the image formation works is essentially our eyes think light has traveled in straight lines. So essentially what we can do there is draw one of the rays of light that's gone back, continuing that line straight on, and then show the original ray which would form that one. And we can do the same thing with the other one as well. Again, our eyes typically think that essentially light continues in straight lines. So one of our lines we're going to continue straight on, the other one we'll draw the light ray that's actually been reflected, and that's how I actually constructed this ray diagram. I could have done this entire process the opposite way round, but I find it easier to do this way. For the virtual images, what I'm going to do is the same process I've used before. Do the ray that goes through the principal focus, the ray that goes through the center of the lens. We see they don't converge, so we extrapolate them back, and then we stick in the virtual image formed. So both of these images, as it says in the question, are virtual types because no light rays actually converge where the image is formed. So what is meant by a virtual image? Well, it means that no rays from the object actually pass through the image. Or another way of saying that is we can't project that image on a screen. So some other similarities between the images. Well, we know they're both virtual, but we need more than that. We can see they're both upright, so they're not upside down. That would be one we could go for. And in terms of differences, mirror image is the same size as the object. The lens image is clearly larger. The mirror image is the same distance from the mirror as the object. The lens image is much further from the lens than the object is. Those are the ones that I would pick up here. Okay, so in the space below, draw a diagram to represent a sound wave. So there we go. Here's a sound wave. We could also represent it with a spring if we wanted to. And we want to label 2 consecutive compressions. There we go. 2 consecutive rarefactions. There we go. And the wavelength, I always draw a wavelength from the centers of compression to the center of the next compression. So there's our wavelength. So now we're looking at the electromagnetic spectrum. Label the positions of gamma rays, visible radio waves. So gamma rays are the highest frequency, visible light comes in the middle, and then our radio waves are our lowest frequency electromagnetic wave. So that kind of answers question 2. It's our radio waves. They have the longest wavelength, but the shortest frequency, but all of these travel at the same speed, 3 × 10⁸. State an approximate value for the speed in air of radio waves. Well, 3 × 10⁸. Every electromagnetic wave travels that speed in air. So we're now looking at the dispersion experiment because we've clearly got a prism and some monochromatic light entering. So what is meant by monochromatic? It means light made of only one wavelength. Literally it means one color, but what we actually take it to mean is exactly one wavelength of light. So the refractive index of glass is 1.49. This keeps coming up, this 1.49, but fair enough. Use the information to calculate the angle of refraction at F. So we're going to be using Snell's Law. We want the angle of refraction, so I make sin r the subject. Sin r, we know the refractive index, it's initially in glass, so we know n1 is 1.49. We can see from the diagram the angle of incidence is 30, and we can get sin r and then do inverse sine and get the angle of refraction is 48 degrees. So let's go back to the diagram and actually draw that on. So this is the one we draw, and we can see it's bent away from the normal because the angle of refraction is 48, whereas the angle of incidence is 30, so it's bent away. Okay. So, state how the refraction starting at F would be different if the monochromatic ray were replaced by a ray of white light. Well, what would happen here is the white light would split into a full spectrum at the boundary. Well, that is greater than the critical angle, so it's going to be totally internally reflected. Okay, so the diagram shows a drawing of plane waves, which means where all the wave fronts are parallel to one another, approaching a gap in a barrier. Okay, so we can see the gap is about the same size as the wavelength. So what we're going to do is we're going to get maximum diffraction. So we're going to get semicircular waves coming out, and the wavelength should still be the same. We haven't changed medium, so the wavelength shouldn't have changed, but we've now got these semicircular wave fronts. It's had maximum diffraction here. So the waves approaching the barrier have a wavelength of 2.5 centimeters and a speed of 20 centimeters per second. Calculate the frequency. So here what we're going to be doing is using the wave equation and rearrange to make frequency the subject. I've converted both into standard units, so it's 0.2 meters per second and 0.025 meters wavelength. I didn't actually need to, but I always work in standard units, giving us a frequency of 8 hertz. So frequency is not affected by any process that can happen to a wave. So the frequency of the diffracted waves is also going to be 8. If they've been refracted, it would still be 8. If they've been reflected, it would still be 8. Frequency just doesn't change with any wave process. Speed and wavelength can sometimes change. So we've got a cross-section through a swimming pool, and we've got 2 light rays striking the boundary. We've got monochromatic light again, so we can put in our definition, it's light of only 1 wavelength. So water in the swimming pool has a refractive index of 1.33. Using the information, calculate the angle of refraction at A. So again, we're going to be using Snell's Law, and 2 this time is going to be 1 because it's going into air. We can calculate sin r and then calculate r, so using the same stages as before. So now we're actually going to put this onto our diagram. So it's going to go into a lower refractive index medium, so it's going to bend away from the normal like you see. Okay, so the critical angle is 48.8. Another ray strikes the surface at B as shown in the diagram. State what happens to the light ray. Well, it's going to be totally internally reflected because the angle of incidence we can see on the diagram is greater than the critical angle. So we can add this onto our diagram. Total internal reflection works the same way normal reflection does. Angle of incidence equals angle of reflection. Okay, so state the type of electromagnetic radiation used in luggage security checks. Those are X-rays, because they need to penetrate all the different layers of stuff. The remote controls for TV sets are typically infrared, as are things like that control anything remote control really. Electromagnetic waves used in a microwave oven have a frequency of 2.45 times 10 to the 9 hertz, or 2.45 gigahertz if you like. The speed of the waves is 3 times 10 to the 8 meters per second. What is the wavelength? We can use the wave equation here. We can rearrange to make wavelength the subject, plug the numbers in, and we get 0.12 meters or 12 centimeters if you prefer. So blending together some thermal physics and also waves, we've got a 150 gram block of ice at 0 degrees placed in an oven. The input power of the oven is 1100 watts. Energy absorbed by the block is 65% of the input energy. Calculate the time taken to melt the ice to water at 0 degrees. Specific latent heat of fusion is 330 joules per gram. So first let's calculate how much energy is required to melt the ice using Q equals ml. And now we know it's a 65% efficient oven, so to get the actual energy we've put into the oven, we need to divide that by 0.65. Then we're going to use the equation E equals PT. We want time, so we can do the energy divided by power. So it would take 69 seconds to melt our ice, so that's going to be just over a minute there. Some components of the electromagnetic spectrum in order of decreasing wavelength are shown. State the speed at which all electromagnetic waves travel in a vacuum, 3 times 10 to the 8 meters per second. State which components of the spectrum has the lowest frequency, that's radio waves, they have the longest wavelength, lowest frequency. 2 components of the electromagnetic spectrum are not listed. Which ones are we missing? So we've got radio, microwave, we don't have infrared, we've got visible, UV, and we don't have X-rays. And then we have gamma rays. That completes our set. Final question looking at microwave ovens. So we've got the inside coat, and then we've got it coated with a metal mesh. The metal mesh prevents microwaves from escaping by reflecting them back into the oven. Suggest one reason why it's sensible to prevent microwaves from escaping. So I can think of 2. We want to improve our efficiency. If microwaves are escaping, they're not heating the food, so that makes it less efficient. And also we don't want living organisms, or more specifically the cells of organisms, absorbing the microwaves. It's not immediately dangerous, but if they heat up enough, that can cause the cells to burst, which is fairly dangerous. And then state one further application of microwaves other than in microwave ovens. Well, I can think of 2. We use them for communication, with satellites if we want to send a signal into space, and we also use them for Wi-Fi. So anywhere that's got a Wi-Fi network is using microwaves to send that information.